time, we're going to talk about the Pendulum lab. In this lab, we consider a simple system which consists of a small steel ball attached by a string of length L. So what do we know about the system? So first of all, we can characterize the length of the pendulum by simply measuring this length L by using a simple ruler. Another important parameter in the system is the angle by which we decline our pendulum. And in this particular lab, we're going to use small angles, and I will explain later the reason behind it. So if we move our pendulum to this position by some small angle theta and then release our pendulum, then it will start swinging. And another important parameter which we can characterize the system is called the period of oscillation, or we'll call it T. So the period of oscillation is the time it takes for the pendulum to complete one full swing. So one full swing is when the pendulum goes to the other side and comes back. So this is our full swing, and the time it takes for the pendulum to go all the way here and back is called the period of the pendulum oscillation. So, and we know a very simple formula which describes the dependence of the period of oscillations on the parameters of our pendulum. And the period equals to 2 pi square root length of the pendulum L divided by the acceleration due to gravity. And you can see that period of oscillation actually doesn't depend on the angle by which we decline our pendulum, and this is going to be true only in the case when we use small angles, because this equation has been derived in the small angle approximation, and that's very important to remember. This video is based on general physics labs which are taught at Stony Brook University, but any pendulum lab is going to follow pretty much the same procedure. So our lab will consist of 3 parts. In the first part, we will measure the period of oscillation of pendulum, and we'll estimate the uncertainty in this measurement, or how precisely we can measure the period of oscillation of the pendulum. In the second part, we'll study the dependence of the period of the pendulum on the angle with which we decline our pendulum. And the third part is going to be the longest part, and we'll study the dependence of the period of oscillation on the length of the pendulum, and then we will calculate acceleration due to gravity based on our measurements. So let's begin by measuring the period of oscillation of pendulum. And this is going to be done by using a simple stopwatch, but we want to make a very precise measurement of the period. So in order to increase the precision of our measurement, instead of measuring one short period of oscillation, we're going to measure 10 periods, and then we'll divide the measurement by 10 in order to find one period of oscillation. So this measurement will be done at the fixed angle, and you want to keep the initial angle of the pendulum fixed for every measurement in this part of the lab. So for that, you will move your pendulum to a small angle, and you will measure this angle using a protractor. So in this case, you can see that I'm using an angle of 30 degrees. So what we'll do, we'll time 10 periods of our pendulum, and we will perform this measurement 5 times. So let's say I measured 10 periods of oscillation of the pendulum, and then I got 5 different results for this measurement. So it was 14.3 seconds, and then let's say the second measurement was. So we have 5 different measurements of 10 periods of oscillation. So let's find an average of this measurement. So that's very easy. We're going to add up all these numbers and divide by 5, since we have 5 measurements all together. So an average of 10 periods equals 14.3 seconds plus divided by 5, and we get 14.5 seconds. So now let's find an uncertainty of the average of this measurement. And for that, we will use the standard deviation rule. You can check out our other video which discusses how to find uncertainty in average. And here I'm just going to write it out. So uncertainty in average equals a square root. We will take our first measurement, 14.3 seconds, and I will subtract the average from it, 14.5 seconds, and then I will square this value. And then I will add another term like this, but this time I'm taking the second measurement. And then I will divide by the number of measurements, which is 5, and multiply by 5 minus 1. And we get an uncertainty in 10t average equals to 0.2 seconds. So now we found an average in 10 periods. So let's find the value of one period, and this is very simple. We will just take our average in 10 periods and divide it by 10. So 14.5 seconds divided by 10 is just 1.45 seconds. And the last step in this part of the lab is finding the uncertainty in one period. And this is very easy because we found one period by dividing the measurement in 10 periods by 10, and 10 is just a constant and it doesn't have an uncertainty. So that means that uncertainty of one period is just an uncertainty of 10 periods average divided by 10. So 0.2 seconds divided by 10 results in 0.02 seconds. And the answer for this part of the lab is that the period of one oscillation is just 1.45 plus minus 0.02 seconds. In the second part of the lab, we will study the dependence of the period of oscillation on the initial angle of the pendulum displacement. And we will see that for larger angles, the period doesn't behave the way we expect it to. So in this part, you will measure 10 periods of oscillation by starting different angles for each measurement. So let's say we do one measurement with the initial angle of 15 degrees, and let's say our measurement of 10 periods in seconds turned out to be 10.1 seconds. And then we do another measurement at 30 degrees, which let's say turned out to be 12.3 seconds, and at 80 degrees, 14.2. So you can see actually that the number for 10 periods increases as the angle increases. Even though from the equation which we discussed above, you wouldn't expect any dependence of the period on the initial angle. So this part doesn't require too much calculation, but the tricky part is how we calculate uncertainty in this case. So uncertainty for 10 periods this time cannot be calculated the same way as it was calculated in the previous part, because we measured 10 periods only one time for each angle. So we don't have those 5 measurements which we had before, and we use the standard deviation formula, so we cannot use this anymore. So now we need to think, where does the uncertainty in this measurement come from? So the uncertainty comes from your reaction time. So when you click your timer in the beginning and at the end of your measurement. So let's say your reaction time is 0.1 second. So you have an uncertainty in measurement in the beginning, which is 0.1 seconds, and you have an uncertainty in your measurement at the end, which is also 0.1 second. So then the uncertainty in the measurement of 10 periods is going to be a square root of uncertainty in measurement at the beginning plus the uncertainty at the measurement at the end. I'm going to plug in the numbers, so square root 0.1 seconds squared plus 0.1 seconds squared, which gives us 0.14 seconds, and this is the uncertainty for every measurement of 10 periods, so we can fill out this column of our table. Uncertainty in 10 periods is 0.14 seconds for every measurement. So in the next step, we're going to calculate the value of one period, which is just, we'll take this column and we'll divide it by 10. And as we discussed before, the uncertainty in one period is just the uncertainty in 10 periods divided by 10. So uncertainty of one period in seconds is... So the conclusion for this part of the lab is that even though, based on the equation, we don't expect there to be a dependence on the angle for the period of oscillation, we do see this dependence, and the reason for that is because the equation which we discussed before was derived in small angle approximation, so it is not valid for large angles. So in the last part of our lab, first we will measure 10 periods of oscillation of the pendulum for 5 different lengths. So in this part of the lab, you will always start your pendulum at the same angle. So pick the angle you like, let's say 15 or 30 degrees, and just stick with it for every measurement. And then you will do this for different length of the pendulum. So let's fill out this table of data together. So let's say we will record the length of our pendulum in meters. And let's say the first measurement was done at 0.1 meters, and you measured 10 periods in seconds to be 6.5 seconds. Then we do the same measurement at 20 centimeters. So now let's discuss the uncertainty in your measurement. So the uncertainty in length comes from the way you measure the length of your pendulum, and it can be estimated as the smallest increment on the ruler, which is 1 millimeter. Or sometimes you'd like to take into account the way you measure the length. So if you take the length measurement from the beginning of the string to the middle of the ball or to the beginning of the ball, so you can also estimate the uncertainty based on the way you measure the length of the pendulum. And let's say in our case, we'll take the uncertainty in the measurement to be 1 millimeter. So it's 0.001 meter. We took an uncertainty as the smallest increment of the ruler, but of course that will depend on the requirements from your TA. The uncertainty in measurement of 10 periods is the same uncertainty as we found in the previous part of the lab, because we did one measurement of 10 periods for every length of the pendulum, and we determined it from our reaction time. And if you remember, in the previous part we got the uncertainty to be 0.14 seconds, and that was for each and every measurement of 10 periods. Now we can calculate the value of 1 period and the uncertainty in 1 period. Now we need to find the period squared, which we will need in order to complete the last part of our lab. So let's calculate period squared, and the units of it is going to be seconds squared. And now the last part of this table is calculation of uncertainty in period squared, and again the units are going to be seconds squared. In order to calculate the uncertainty in period square, we need to remember the formula for the uncertainty when we have a measurement a to the power n. So then the uncertainty in value s, relative uncertainty, is going to be equal to the absolute value of the power n multiplied by relative uncertainty in your measurement a. So how do we apply this formula in our case? So in our case, our S is our period squared because that's what we want to find the uncertainty of. And the measurement A is just the period. So knowing that, we can find relative uncertainty in T squared. So I'm just plugging in T squared equals to the power n, which in our case is just 2, multiplied by the relative uncertainty in period, so uncertainty in period over period. And now I can multiply both sides of this equation by t squared, so I get the uncertainty in t squared equals to 2t delta t, and I will do an example calculation for the first measurement. So for t, I will use 0.65 seconds, and for the uncertainty, I will use 0.014 seconds. So the uncertainty in t squared equals 2 times 0.65 seconds times 0.014 seconds, which results in uncertainty of 0.018 seconds squared. So now I can fill out the last part of our table. And also, you will notice here that the value of uncertainty increases as the value of t squared increases, because in order to calculate uncertainty in t squared, we multiply by t itself. So as t increases, t squared, the uncertainty in t squared increases as well. Now let's use the data which we collected earlier and summarized in our table above to find acceleration due to gravity, g. You may ask why we find an acceleration due to gravity if we know the value already. Well, that's the whole point of the lab, is to find something which we know already so we can compare with a known value and see if our experiment was correct. So let's look back on the equation for the period of the pendulum oscillation. And you can see that we have acceleration due to gravity here in denominator under the square root. So let's play around with this equation a little bit, and let's square both sides of this equation. So we get t squared equals to 2 pi squared multiplied by the ratio between L and G. Now let's rearrange this equation a little bit, and I'm going to write it as t squared equals to 2 pi squared over G times L. Now let's think of an equation of a straight line, y equals mx with the zero intercept. So we know that m is our slope of a straight line. So now let's take a look at our equation and notice that if we plot the length of the pendulum on x-axis and t² on the y-axis, then our slope will be equal to 2 pi square over g. So if we know the slope of this line, we can actually calculate from the slope acceleration due to gravity. So how would we find this? The slope would be equal to 2 pi square over g, or in other words, acceleration due to gravity will be equal to 2 pi square over slope. So once we find the slope of the graph, we can calculate our acceleration due to gravity. So you can see here that I already put our measurements from the table on this axis, and notice that I put the values of the length of the pendulum on x-axis like we discussed before, and the values of the period squared on y-axis. And the most important thing to remember in your lab report is always label your axis and don't forget to put the units. And same is here for y-axis, you have period squared and second squared. So you can see that I put all of my points together with the error bars, and all error bars are to scale. So you can see that t² errors are increasing as we go to higher values of the period. So now what we need to do is to plot a best fit line to this point, and we know that the period is going to be 0 if the length of the pendulum is 0, so our plot has to go through 0, 0 point. So I start at 0, 0 point and I draw a best fit line, and it's going to be something like this. So if you prepare this graph on the computer, it will give you the value of the slope right away. If you draw it by hand, in order to find the value of the slope, you will have to pick 2 points on your graph. So let's say point somewhere here and point somewhere here. Ooh. A little crooked. And then using these 2 points, you can calculate the slope of this plot. So for example, this is point 1 and this point 2 and this point y1 and this point 1, 2, and then the slope will be equal to y2 minus y1 divided by x2 minus x1. In our case, slope equals to 4 seconds squared per meter. And you can see that the value of the slope has units, and it's seconds squared per meters because units of y are seconds squared and units of x are meters. All right, so that was the best fit line. But now we need to take into account the fact that our data points have uncertainties. So the maximum slope of the fit could have been something like this. And we can calculate the slope of this blue line. So I will call it slope maximum. And let's say it turned out to be 4.55 seconds squared per meter. And then another worst case scenario is when we have a minimum slope, which will go something like this, including the bottom line, and the slope minimum is going to be something like 3.75 seconds squared per meter. Now, using the maximum and minimum slope, we can calculate uncertainty in the slope. So uncertainty in slope will be equal to slope maximum minus slope minimum divided by 2. So then we have 4.55 seconds squared per meters minus slope minimum 3.75 seconds squared per meters divided by 2. And uncertainty in the slope equals 2.4 seconds squared per meter. So acceleration of gravity from our slope is 2 pi squared divided by the slope, which is 4 seconds squared per meter, giving us a great value of 9.87 meters per second squared. Hey, that's pretty good. Now we can calculate uncertainty in g, and we know that g is 2 pi squared divided by slope. And here we can use a product rule. So what is a product rule? So when S equals to A times B, or S equals A divided by B, which is our case, then uncertainty in S, relative uncertainty in S, equals to square root relative uncertainty in A squared plus relative uncertainty in B squared. So we will be using this equation, and in our case, A is going to be equal to 2 pi squared, which is a constant and doesn't have an uncertainty, and B is going to be equal to our slope. So we know that S equals G, so then relative uncertainty in G equals to square root. So uncertainty in 2 pi squared is 0 divided by 2 pi squared, which is just 0, plus uncertainty and slope, which we just calculate 0.5 seconds squared per meters divided by slope 4 seconds squared per meters squared. And here we get 0.1, which is a relative uncertainty in G. So multiply both sides by G, we get uncertainty in G equals to 9.87 meters per second squared, multiplied by 0.1, which we just found, which gives an uncertainty of 0.9 meters per second squared. So the answer in this case for G is 9.9 plus minus 0.9 meters per second squared. So now the final step to this lab is to make a conclusion. Does our value agree with predicted value of 9.81 meters per second squared? So let's compare them, and we will do it in a very nice way. We will draw a number line. Let's put our measurement on the number line. So it's 9.9, which is somewhere here. And let's add the error bars here. So 9.9 plus 0.9 is going to be 10.8. So it's somewhere here. And minus 0.9 is going to be exactly at 9. So our experimental values are somewhere between these two lines. Very messy. And now, where on the number line can we find our expected value of 9.81? Well, that's somewhere here, right? Somewhere here we have G equals 9.81 meters per second squared. And you can see that this value actually falls within the range of uncertainty for the measurement we found. That means that our value is consistent with the predicted value. Perfect. Good job.